Okay, so today we're going to do modeling data in the organization. We'll get through about half this lecture. The first half of it is a whole bunch of explanatory material. The second half is basically a bunch of practice problems, and examples and such. So we'll talk about the principles today. We'll do the other half on Thursday. Our learning objectives, terms, data modeling, good names, definitions, unary, binary, ternary relationships. In case you don't know, unary, that means single, right? Binary is a term I hope you're all familiar with, meaning, basically combination of two things in some sense. So unary is basically recursive. A thing links back to itself. And ternary, turn for three, basically a three-part relationship. All right, we'll model different types of attributes, entities, relationships, and cardinalities, convert many-to-many relationships to associative entities, and eventually do some timestamp stuff, which is about as simple as you think, right? Basically, you have a thing, you put a timestamp on it to show when it was. And that's good for different kinds of versioning. For example, one spot where timestamping is actually used, when Google stores a copy of a database, a copy of a web page in its database, it may often have multiple different versions of that web page from different times. So it'll have the page and all of its associated data, and then it'll also include a timestamp field in the table to, be able to recognize when it was from. So if it wants to pull the most recent version or an older version, it has that capability. Okay. So all this stuff that we're going to do today pretty much comes from this analysis section. And remember, we talked about the other day, SDLC, right? System design lifecycle. We go through this kind of circle. We make some plans, we analyze it, right? So the plan is basically very much a big picture idea. Analysis, we're sort of getting into the details. Design, we're making a specific implementation plan. So what database is going to be written on what hardware and what software version, and what version of SQL is it going to use, stuff like that. Eventually you implement it, right? So once the plan is complete, you know all what you're going to do, then you go ahead and do it in the real world, see how it goes. And then maintenance. Maintenance includes things like review, updates, all that stuff, okay, which can, again, launch a new cycle. So part we're going to talk about is what's called entity relationship modeling. So the idea of entity relationship modeling is there are two things we want to model. Number one, entities, the actual things that we're going to model in our database. And then relationships, the relationships between them. I'll move this over so it's a little, let's see, how can I put this in a better way? Is this better? It's a little better. It's still terrible. Okay, let's shrink you a little bit then. Come on, there we go. All right, that's good, that's decent. Okay, so those are the things we're going to cover, right? Basically, entities and relationships, and every entity can have a set of attributes. So, for example, let's do a simple practical case. That's some stuff from Java earlier today. So, suppose we wanted to model a set of courses, students, and instructors, okay? And we have some detail on this, right? Every course is taught by at least one instructor, okay? Every course may have students, okay, but, not necessarily have any. When would a course not have students yet? When you first list it in the system and nobody's registered for it yet, right? So you don't want to have the case where a course is required to have one student, because then that would invalidate the launch process. Okay, but we can say that a course, when it's entered into the system, will have at least one instructor. Because at the time that you enter the course in the system, you have a plan for who is going to teach it. And that might be, essentially a business rule, a practical rule of how you set this up. And what else? Courses, students, instructors. Well, that's pretty much it. Then we can talk about attributes. Oh, so let's say instructor for purposes of our database has a name and maybe a department. Maybe we track that as well, right? Course will have a name. We'll have what else? An assigned room and meeting time, right? Whatever that may be, like Monday, Wednesday, Friday, noon. Okay, and what else? A student, right? Student will have a name and say a UIN, possibly a major, if we wanted to track these things. So the question, right? So these things, the things we are modeling are entities, right? And when we mean entities, entities mean general, abstract things, not specific ones, right? So we have instead the idea of a course, not a specific course, which would be called an instance, right? An instance of a particular thing. The relationships are the connections between the entities. So, for example, all these business rules, right? So every course is taught by one instructor. So that would mean a course would have an instructor field, which would link to the instructor entity, right? Likewise, that was weird. Okay. Likewise, a course might have a set of students, each one linking to a student entity. Okay, so that's the idea of what we're doing here, entity and relationships. Now, it's worth mentioning, we will cover all this in the context of relational database systems. Okay, but relational databases are not the only place where enterprise relationship concepts are used, right? You can have other types of databases, entities. Anytime you have a database, in some sense, you're definitely going to have things that you want to relate to each other. And you're also going to potentially have different kinds of relationships. But what we're doing here is definitely geared toward this relational database model. So that's the idea of what we're covering. So sample ER diagram. Excuse me. I'm going to zoom in on this a little bit so y'all can see better. Okay. So in this case, these squares, the big squares, those are our entities. And these are the things that we're trying to represent and track in our system. So first one is supplier, right? Supplier is someone who sells stuff to you, right? They're like a vendor. Suppliers generate shipments that arrive at your operation. Likewise, you have customers. Customers place orders. Those orders are for products, right? You can have many items in a shipment. All right. So the boxes, like you can see the key below, the boxes are the entities, the things that we're going to model in our database. The relationships are the lines between them. And then we have what are called cardinalities, basically how many things we're talking about. So, and whether they're mandatory or not. So let's look at this crowfoot notation a little bit. Let's go just straight left to right, supplier and shipment. Okay, so every shipment must be sent by a supplier, right? So we see this mandatory one. So the point next to the supplier, that's the relationship between the shipment and supplier. So every shipment is sent by a supplier. You can't have a shipment that comes from nowhere, right? It has to come from a supplier, and it also has to come from exactly one. Each shipment arrives from exactly one supplier. So when we see this double line, mandatory one, exactly one means the same thing. On the other hand, a supplier could send many shipments over the course of our tracking. So we see the crow's foot, right? It's one to many. Also, it's optional. A supplier does not yet have to have sent any shipments. So you could add a supplier to your system, and perhaps a shipment takes weeks, months, perhaps never arrives. Perhaps the supplier never actually sends us anything, but they could still be in the database. Or, you might add a supplier and the same day they send a shipment. But the point is, a supplier can exist in your database system even if it hasn't yet sent any shipments. But once it does exist in your system, potentially it could send many shipments, which makes sense. Okay, relationship between suppliers and items. This is a many-to-many relationship. Each supplier could potentially provide many different items. And we see here this circle again indicating that it's optional. So a particular supplier may supply many items, but it also might not yet supply any items at all. You might just have a supplier that exists in your system, but you don't have any transactions with it yet. Likewise, each item must arise from at least one supplier, right? So this line here, this indicates it's mandatory, right? You can't have an item that exists in your system unless it's been supplied by a supplier, right? So what our database is tracking are the things that have actually been delivered, not, a wish list of things we might like to have. Likewise, many to many, right? So any particular item could be potentially provided by a number of different suppliers, not just one. And so this is a many to many relationship. Right. These other ones, they're variants on all these same things, right? So each item, may be used in one product. So the products are, the merchandise that we're selling. The items are essentially the components. So whatever our operation is making, say we're making cars, items might be windows, might be wheels, might be engines, who knows? And then ultimately all assembled together into a final product. So each product could use many items. An item could be used in many different products. You might have a whole line of different car models, each of which uses the same kind of tires, for example. All right. An order that is placed for a specific set of products. So you can see here, each order, there's a many-to-many relationship again. So each order has to contain at least one product, but might contain many products. So if we say, hey, maybe this is for cars, you could have an order from a dealership that says, gosh, I want 24 cars to fill out our parking lot. So they place an order for 24 different cars. Or it might be just an order for one car. Likewise, okay, but an order has to contain at least one product. There's no way you're placing an order that's not actually for something. And you might have a product that does not yet exist in any orders, right? So you might have some cars that you finished manufacturing, they're sitting in a warehouse somewhere, but nobody's actually ordered them yet. Okay, so, and then customer, every order has to be submitted by a customer, right? Because unless a customer has submitted the order doesn't exist. But a customer can exist in your system and have not yet submitted any orders. That's why that's optional. Okay, so this is kind of a detailed thing. I wanted to go through all the different relationships here because this is the sort of thing we're going to see more and more of over the next couple weeks, even the rest of the course to some extent. So it's worth going over. All right, questions on any of this? Any part of this not make sense? All right, Mr. Faroon, I'm gonna mute you. I don't know if that was intentional or not. So questions, or should I move on? I'm going once, going twice. Okay, gone. Fine. All right. So the basic ER notation, that's what this is. I guess I'll unzoom it a little bit. It's kind of big now. There we go. Okay, so there are three different types of entities. First type is a strong entity. Strong entity basically exists on its own, does not depend on the existence of something else. A weak entity is essentially something that, as far as our database is concerned, only exists in the context of a strong entity. And we'll have an example of that, but the one they give is essentially you can have employees and those employees can have dependents. So employees would be considered strong entities. They can exist in your system regardless of anything else. But the dependents of the employees, those are considered weak entities because you would only record a dependent in your system in association with a particular employee. And an associative entity is something that exists as the combination of other factors. So we'll have an example for that as well. Okay, but they do one with qualification courses later in the slides. Okay, let me put this in. Let's see, somewhere in here we're going to start seeing. There we go. Okay. So suppose you have a call center and you're tracking phone calls, right? Basically for customer service. So the persons would exist because they placed the call. Okay, so any list of whoever it is, customers, employees, whoever's placing those calls, those people already exist in your database system. However, a phone call from that person would be considered a weak entity because you're only going to track a phone call in conjunction with a particular person, an instance of person. Okay. So some different models for these. Let me go back one. This is a unary relationship, and it seems strange. We'll talk about this on the next slide. But unary means a particular person is related to another person. For example, suppose you have a phone call between two different people, right? So every phone call contains two people. Well, then that might be considered sort of a unary relationship in that every person in that phone call is related to the other person in the call. You might have a binary type situation where you have something that involves two different types of entities. For example, suppose you have person is considered to be someone who attends an event. Now, you might have the event attached to an entity called location, right? You might have different conference rooms, for example. An event might be the combination of a particular set of people at a particular location. And you might have some other things, for example, where you have the interaction of consultants, clients, and contracts all coming together as, essentially some plan, some agreement, whatever. So every contract, it has its own document, but it also has an association with the client, the person, the customer who's buying it, and your consultants who are working on it. So these are more interesting kinds of relationships that, advance into these kind of things. All right. So unary relationship, let's give examples of all of these. So the unary one is really the weirdest. It's hard to understand unless you've actually taken a little time to think about it. But one example of that is with subsets. Okay, so imagine if you have some set of, this is a good one, graduate students and teaching assistants. Okay, so at UIC, almost invariably, teaching assistants are graduate students, but only a small fraction of graduate students are, in fact, employed as teaching assistants. So you might have a relationship between a kind of table where one set of users is teaching assistants and another set of users, another set of people are just ordinary students. But every teaching assistant, since it is a student, would be linked back to that original teaching assistant, be listed back to that original graduate student table. Binary one, that the easiest way to think about that is essentially where basically a relationship between two things. For example, if you have a table of addresses and every address contains a zip code, you might have another table for zip code that contains the zip code and the municipality. So that would be a binary relationship. There's two separate tables containing separate things, but they're somehow linked. And a ternary relationship, what's going on here? Yeah. A ternary relationship, again, three different tables that are in some sense related. And that goes back to this very first, no, I don't want a lunch launch server. This first example we did with courses, instructors, and students, right? So depending on how we were setting this up, these might all be as different tables, right? And then the combination of these things might have some meaning, okay? But we would have to have some point in the middle where they all match, where they all link up. All right, this is, if this seems a little bit confusing, yeah, this is why entity relationship modeling is, there's a little bit of an art to it, right? There's a little bit of, there's always choices that can be made, and some of the choices are better than others. Okay, so, but right now, where we're at, again, basic drawing with cardinalities with relationships between entities, and then this different relationships between the entities and basic notation. Okay, we'll have some more explanation in a moment. Now, when we do the modeling, we want to make sure that our database is based on reality. Basically, it models the things we want to track in the way that we want to track them. And the way we want to track them is in line with business rules. So business rules are these kind of statements that define how the various entities are involved with each other. So they say here, statements that define or constrain some aspect of the business are derived from policies, etc., and assert the business structure. So examples of business rules, this sort of thing. Every course is taught by at least one instructor. That's a business rule. That's just a setup of how things are at UIC. Okay. We might also say, of course, may have students, but not necessarily have any. Well, when we first, this is a modeling choice. Do we want to ensure that a course is only reported in our system after it's come to pass and it's had some students in it? Or do we want to allow courses to be entered into our system and made available for registration, even though they don't have any students in them? Yes, right? In them yet. And I think in most cases, that second example would be the one that makes the most sense. Okay. So one thing, in general, there are going to be way more business rules than you can implement in a database, right? Obviously, businesses have all kinds of these rules, untold, vast lists of these kind of rules. But when you're talking about how specifically you want to implement things in your database, well, the question is, what things are we going to implement in the database, and how are we going to implement them in a way that makes sense, as far as how we run our business? Okay. Yeah, what you got? Sounds like humming. Okay, we good? People occasionally bump that. Cool, just scrolling through. How y'all doing? Okay. So they give a little bit here about good business rules, essentially. The big things, single statement, precise, everybody understands what they mean, consistent with actually how you do business, that sort of thing. Okay. And this is a big part of the analysis stage. They talk about this a little bit in the textbook. They say, hey, you have this planning part where you want to figure out, in the planning stage, you figure out what things to be tracked in your database. And in the analysis stage, you go through different how you are going to track them. I feel like there ought to be a button that I can just mute everyone. Let's see, who's here? Who keeps? I guess. Okay, whatever. So, but we don't have to beat that thing into the ground. Hopefully it's something you all understand. That the part is first figure out what entities you're going to model in your business, have an idea of the relationships between them. Then you further clarify by following business rules, right? And that's where we get into all that sort of things like in this diagram here, where we say, gosh, supplier, every shipment has to be associated with supplier, but you can have a supplier doesn't yet have any shipments. Okay. Another thing, just good practices for names, right? So anytime you're thinking about names for entities themselves or the fields, generally it's good practice to use common words that everyone will understand, because you don't necessarily want to limit your database to just specialists. Okay, so they say all these factors here. I guess if it comes up on an exam, you can, look it up from this slide, but, just keep things simple so that everyone can understand what you're talking about. And also it ought to have some, meaningful understanding within the business. For example, if you say, our database should have a customer entity, right? That might mean different things to different departments. Okay, so what would it mean to marketing or to the manufacturing or to operations or to finance, right? In different contexts, it might mean very different things. Marketing, presumably individual customers you're talking to, right? So for marketing, perhaps customers in a CRM, customer relationship management system, right? Basically, people who have already bought your goods. For operations, perhaps it means specifically wholesalers, not individuals, right? A lot of manufacturing operations, they don't sell direct to the final customer. They sell to basically a warehouse type operation called a wholesaler, which then sells quantities somewhat in bulk to retails, right? Ordinary stores, which then sell the items individually to customers. So for operations, maybe their customers are these wholesalers, right? Definitely not individuals. And for finance, perhaps it means something totally different and unrelated to, selling products, right? But perhaps something else. All right. So again, these terms that you come up with in your database, it might sound obvious. Oh, I know what a customer is, but different people at different points of the organization might have a different understanding of what these things mean. So it's important to clarify all of that. All right. Data definitions. So every time you're keeping data in your database, you have to do it within some kind of framework. One part of that is terms and facts. So a term, of course, word or phrase with specific meaning. You might say, that's a customer. Customer is a term. And a fact is some kind of association between these two or more terms, right? So basically what we're talking about here is business rules once again. So you might say, again, every customer, every order has a customer. Well, once you've clarified exactly what a customer is for your database, and once you've clarified exactly what an order is, then you can come up with the fact that that's what the association is. The association, every order is placed by a customer, for example. Okay, again, guidelines for good data definition. They should be concise, should be easily understood. They say here, gathered in conjunction with systems requirements. So part of the discussion stage before you're actually trying to implement the database. Diagrams, because people understand pictures well. And again, talk to a bunch of people, figure out exactly what you mean when you say customer and exactly what you mean by order. Now, again, customer and order, they're pretty straightforward, pretty, easy to understand once you've agreed on what these things are. But imagine if you're talking about inventory, right? So you're selling cars. What data fields should be contained in a car? Ooh, that's not good. In a car entity. Make, model, base cost, selling price, right? Dealership, what else? I don't know. Any number of things, right? This is part of the data clarification process. This sounds kind of ominous here, right? The person who knows the meaning of data controls data. I don't know. That seems like it's trying to scare people. Okay, so that's all that would normally come up within the planning stage. All right, we have somebody's having microphone problems. What's going on? Oh, hello, Marilyn. I'm going to mute you. Zoop. Okay. I imagine some people are probably listening on phones. And that's the source of this bumping, perhaps. I don't know. Maybe whatever. Okay. So back to entities. So remember, an entity is basically the thing that users want to track in their database. So they say person, place, object, event, concept, whatever, any kind of things you want to include. Okay. Entity type, collection of entities that share common properties or characteristics. Right. So for those of you who have taken Java with me, one of the things we talk a little bit about is inheritance. Right. So you can have things that are essentially subclasses of other things. For example, this thing went very wrong today. I don't like Windows 11's version of Paint. It does this checkerboard stuff in the background. Okay. But imagine if you are doing some kind of inventory tracking system. You have an inventory tracking system, and you might say, basically, you are selling vehicles. So everything you're selling is all for products are vehicles of some kind, right? But they could include trucks, could include SUVs, could include regular cars, right? Other things, who knows what. Okay, they're going to certainly have some common attributes, right? All your vehicles are going to be some kind of one of these specific instances. So you might say, for example, just hypothetically, you have vehicles that are for one category is for passengers, and the other kind is for shipping, right? Cargo, I was going to write, but shipping. So you have different categories for all these. So all of your vehicles that you have in your system are either shipping or passengers, right? So maybe for shipping, you have vans and you have 18-wheelers, right? The big trucks. Those are your two categories there. For passenger vehicles, maybe you have, lost track of the cursor here. There we go. You might have compacts. You might have just what we'll call cars in our system. You might have SUVs, right? And all of those are going to be separate ones. And the modeling will be assumed that if your passengers and shipping are both kinds of vehicles, whatever attributes vehicles have, things like size, weight, fuel capacity, number of tires, whatever, all of those passengers and shipping vehicles will both have those. But for shipping vehicles, you might include some specific numbers about cargo capacity, right? For passenger vehicles, you might not. You might include like seating for the number of passengers as an attribute. Okay. So that's what we mean there when we call, entity types. And last, entity instance. An entity instance is a single occurrence of an entity type, or in this example that I just drew, a specific car, right? So we could say here, Honda CRV, number 000001, and then Honda CRV number 000002, ... and so on. Okay, that's what we talk about that's what we mean when we talk about instances, the specific vehicles themselves. So here's some example, right? We have entity type and entity instances. So we have the entity type employee, right? So you might say the overarching entity is simply people or persons, whatever. And some of your persons are employees, some of them might be other people, who knows, right? Contractors, for example, not really employees, but contractors, consultants, whatever. But for employees, you say here are two instances. So the first instance is Michelle Brady. The second instance is David Johnson. And they both have their different attributes. They have different addresses, different zip codes, different hire dates, right? All that. Okay. So generally, when you're defining what should be an entity, some things about an entity. Number one, it should be an object that will typically have many instances in the database, right? Not just one thing, because then that can probably be encompassed by business rules. So an entity is going to be a thing that you're going to have a lot of them in your database. You have a lot of customers, a lot of vendors, a lot of products, whatever. Generally, it will also be an object that has multiple attributes. For example, for employees, you might have name and address and phone number. If they have an office number, stuff like that. And of course, very obviously, your entity should be some kind of object that we are trying to model, right? So you're including in your database for a reason, because it's important. In general, entities should not be users of the database system or outputs of the database system. Okay, those can be handled in different ways, but they shouldn't be tracked as entities. Entities are the things that you're trying to model, not who interacts with the system or what the system produces. Okay, so for example, suppose you have some database system that you're going to track accounts and expenses. So every account has some listing of expenses, right? An account can have one or more expenses. In this case, they're saying, well, you can have a treasurer, and the treasurer can manage a set of accounts, and the treasurer can receive a set of expense reports, and each expense report can contain multiple different expenses. It's true that those are things that the database system might eventually produce, but you don't need to include that in the entity relationship modeling. Okay, it's simply there are accounts, the accounts contain expenses, and yeah, your system can produce some reports, and those reports can be received by people, but most likely that's not something you're going to want to include in the entity relationship modeling process. All right. So we talked before about strong versus weak entities. So a strong entity exists independently of other types of entities, right? It's something that exists on its own in the system. So, for example, your system can have accounts, right? The existence of accounts doesn't really depend on a particular other thing. It doesn't necessarily have to be associated with a particular user. Probably ought to be, right? Every account might have a data field that's required that says, hey, here's the person who's managing this. But the account, it's something that exists independently. Likewise, expenses, right? Expenses arise, they exist independently of whatever account, right? It's not that even though a particular account can be responsible for expenses, can be charged expenses, expenses don't depend on the existence of an account in order to happen. Weak entities, though, weak entities depend on a strong entity to exist. As far as your database is concerned, they cannot exist on their own. They only exist because something else already exists. And so the example they like to give here is for dependents. So you have some set of employees, right? Your business has employees, they exist. That is a strong entity. However, at some point you say, hey, we are going to track a list of dependents for various, sorts of benefits or, health insurance, whatever. And you say, okay, every employee can enter a list of their dependents into our system. Well, of course, a dependent is only considered in the system in conjunction with a particular employee. So And in that case, we say that employee can have a key field as the employee ID. Remember that the key field ensures that every employee instance is unique, because if every employee record has a different employee ID, then of course there's no way that two employee records in that table can have fully duplicate data. On the other hand, a dependent, yeah, the dependent could have a name, but that by itself is not going to be a key field, right? You can have multiple dependents who all have the same name, just like you could have multiple employees who have the same name. So as part of this, the other part of the key would be the employee ID itself. So in this case, the employee key would be employee ID. The dependent key would be employee ID plus the dependent name. And I suppose for that, you would hope that in your database, no employee has two dependents with the same name and the same date of birth, right? I guess it is unlikely, but possible. Okay. Does that make sense? Questions about strong and weak entities. It's one of the weirder concepts because, you know, you could look here at expenses and say, hey, if an expense is actually being charged in the system and it can only be charged in connection with an account, is expense a weak entity? Well, depending on how you're modeling these things, yeah, maybe. Okay. But in this case, we're saying, well, the expenses are, they arise independently. They are their own things, and they just end up being charged to a particular account. But conceivably, it could be the other way. Again, independence of existence, right? So you wouldn't normally, right? The dependent example is clear. A business wouldn't normally track dependents without connection to some employee, right? I mean, that one's pretty clear, right? There would be no particular reason for a business to just track a long list of people that are unrelated to its actual employees. So we could say, for purposes of the database, since every dependent must be linked to a particular employee, right? In a sense, owned by an employee, right? Then dependent is weak and employee is strong. Okay. But again, the expense example is, the expense account example is murky, right? That one is definitely not so clear, because you could say, well, the accounts exist independently before any charges are applied to them ever, right? An account can exist even if it hasn't had any charges placed to it, just like an employee can exist if it doesn't have any associated dependents. But the expenses could go either way, right? Could be strong in the sense that expenses are incurred, but only eventually assigned to an account, right? Then in that case, it goes on. Or they could be weak and domestic nonsense. Or they could be weak and expenses are only created as belonging to an already existing account, right? So it really depends on how expenses are managed in the system. The strong entity model would be, something like employees have expenses, right? Or departments, whoever. have expenses. They enter those. Vivi, please keep quiet. I'm lecturing. They enter those expenses in the system, and perhaps those expenses are eventually approved and assigned to an account. Okay. In that case, that one, the expenses would be strong entities. Right? They exist, have an independent existence before they're ever tracked to a particular account. Okay. So again, like I said, some of this stuff is a little bit murky. I hope, yeah, good. Thank you. I hope that, when time comes around that all this is on an exam, I hope the examples for the exam are very clear. I'll do my part to try to make sure they are. Okay. So, cool. Well, anyway, I hope that helped. All right. So, weak identity with identifying relationship. Okay. So guidelines for naming entities, right? Of course, keep them simple, keep them specific to your organization. Once you've picked a name for an entity, stick with it, right? Don't call it customer in one batch of materials and then call it buyer in another. Things like that are likely. But, this is pretty much common sense. All right. Now, entities have attributes, right? They say here properties or characteristics of entities or relationship type, what we've called data fields, right? But they call them attributes. It's more common in ER modeling. So, basic kinds of attributes. Number one, required versus optional, which we've covered. Simple versus composite. We'll talk about that. Single valued versus multi-valued, stored versus derived, and then if it's an identifier. So, go ahead and get into this. Now, here, suppose we have an entity type student with required and optional attributes. So suppose we're tracking a student at UIC. What are some things that might plausibly be required? I don't want to do this whole thing, but I guess it all kind of blew up there on me. It shows you the final iteration of the slides. So let's talk about UIC though. Students in a database at UIC have presumably optional and required attributes. Okay, so what might be 2 or 3 required attributes for UIC students? Give me some examples. Yeah, right. Sure. UIN. That seems like a sensible one. Email. Okay. I'll say specifically UIC email. And I'll also say or net ID. Well, major, that's an interesting one. Do all students have to have a declared major? See, so that one would be optional. You can be a student, it could be like your 3rd, 4th, 5th, 6th year, and you're just sailing along, taking classes. However, you might not even be on a degree path. iCard. Well, what would be the part? Yeah, so let's say optional, right? Might be major. I suppose college, you join the particular program. But I would say even a degree program for college would be optional, right? Yeah, I'm not sure. Financial support, I'm not sure how that would all work in the database. I could probably think of something. Sure. But I'll say, current courses, right? That would be something. Year of what? Oh, like how many credits? Sure, right? So credits, say even if 0, right? You're going to have some number there for credits. Presumably, you might have some GPA. Again, even if, if it's 0 divided by 0, whatever. Accounts receivable, yep, perhaps. All right. And I'll list here, even if 0. All right. So remember, there's a difference between fields that happen to be 0, meaning that, yeah, like for accounts payable, I guess, or what from UIC's perspective, receivable. Even if the number is 0 there, you would still want to have, a field and there would be some entry in it, right? But it's different from saying there's no major yet. I guess, again, this is really a modeling issue. So we could ask here, is undeclared an option, right? So if you can list undeclared as your major, well, then you might say, well, okay, that's a required attribute, right? The major, because we have an option for undeclared that says, okay, you don't have a major. Same thing for degree program college, right? So yeah, these are some interesting modeling issues. And well, what's fair to say is that an attribute that's optional in some sense could be structured to say it's required, right? To say there has to be some value, but you just have, it's kind of a cheat to say, well, this attribute is required, but one of the options is to say it's not there. Is that the same as optional? Well, functionally, yes. Okay, so anyway, the example they give here, we say, okay, every student has to have an ID, a name, an address, but major is optional, right? This person, Michael Grant, has majored in MIS, good for him. Melissa, she has apparently not yet declared a major, right? So again, this is optional. It's just empty, right? And the system has to figure out some way it's going to deal with that. But if you said, well, there is a major, but it's undeclared, yeah, functionally that's the same thing, but it's not blank. So that's the question. If you say something is required, there has to be a value always. Okay. If it's optional, that basically means you can leave it blank. And functionally, like I said, sometimes those things are basically the same. Composite attributes are attributes that have meaningful component parts. For example, address is an obvious one. You can divide that into street address, city, state, potentially zip code as well, right? And there's different ways to parse that, but an address is inherently a somewhat compound thing. You can also have a multi-valued attribute, right? So this becomes important when we talk about database normalization. One of the things we often try to do with our databases is remove multi-valued attributes. So clearly, employees can have more than one skill, right? If you have some list, here's an employee, here are his skills, you might say something like employee 1 skills, maybe is proficient with Excel, and let's say, I don't know, let's say we're doing a ranking from 1 to 5. Ranked at 4 for that. MS, I don't know. SharePoint, let's say 5. And let's say JavaScript 4. And I don't know, SQL ranked at a 5. Okay. You could do some kind of list like that. And then employee 2 might have a different set of skills because they're a different, they might be a forklift operator, right? Grade 5. Truck driver, grade 5. What else? Probably not a programmer. I don't know. I guess we leave it at those 2. That's fine. Okay, so, but obviously it makes sense if you have some kind of system that employees can have different skills. Now, what you might do is simply, instead of having this kind of multi-valued attribute, you simply might say list E1, right? And you have some separate object in another table that lists these things. And then, it's not really a multi-valued attribute. Then you say, well, we have this one thing here. That's the list, but the list is, a list of multiple things. Okay. The other one, derived. Derived attributes are things that are calculated, right? Things you don't physically store in the database. And those tend to be chronological ones, chronological or other mathematical computations, right? So suppose you want to track how much time, an employee, how long an employee has been employed. You, okay, at the firm. You wouldn't just put that, you know, years number in a field in the database because it would require regular and frequent updates. Basically, every day you'd have to go into your database, scan through, see if somebody's, time at the firm has gone up by a year, and then increment it. It would be better to just record the start date of employment and then subtract that date from present moment to calculate the years employed. And you would only do that as needed, right? So if somebody says, hey, I want to look up how long Joe's been here, well, then you do that database call and you pull that data and your application does the processing on it. Okay. So in general, multi-valued attributes, we try to remove them through database normalization. We'll talk about that as the course goes on. Derived fields, same kind of thing, right? We don't really, most of the time, we don't want to store them permanently in our database. We want to keep the raw data. And if we need to do some derivations on it, like figure out employment history or figure out, hey, is it, how old is this employee? Are they due for some special, benefits based on turning 65 or something? Then we can include that in our database. We just include their birth date. We calculate their status based on that. Okay. So next thing, keys, which we've talked about before, but we're talking about it again. So the identifier or key is an attribute or set of attributes that uniquely identifies individual instances of an entity type. All right. And of course, we have the same thing, simple versus composite identifier. And then candidate identifiers, things that could be an identifier. So I don't want to do it here. Let's talk about key field, what they call primary key in Access. Primary key is the field or fields that uniquely identify records in a table. Okay, so suppose Facebook has a table of users, right? People like us use Facebook. What might be a suitable key field or fields to uniquely identify users? What do you think? Email, phone, user ID, and email. Yeah, potentially any of those could work. Okay. So phone number, email address, anything else? And here I'm saying stuff, stuff that you could use, right? Not necessarily. So email is the one that Facebook does use. What's something else that might uniquely identify humans? Well, probably not name, right? Yeah, I was thinking social security number. So name it is certainly possible that you could have multiple people with the same name, right? So we'll come to that in a minute. So SSN, probably not date of birth, right? So probably not name. Two reasons. Number one, multiple users can have the same name, and more to the point, right? And anyone can claim to have a name, right? You could have 50 people showing up and saying, my name is Fred Zakukibib. And I mean, honestly, how is Facebook going to know? Facebook can check your phone number, right? They can send you a text and say, hey, respond to this if it came in. They can send you an email and say, respond to this if you have access to this email account. Conceivably, they could go through some operation with whatever federal operation manages social security numbers and handle that. But Facebook isn't really going to be able to check your name, right? The other one, date of birth, right? Date of birth, of course, many users could have the same birth date, birthday, including year, right? For example, twins, right? If you have a pair of twins, of course, they're going to have the same birth date. Yeah, various sorts of ID numbers, you could come up with something, right? Anyway, so these are all, yeah, you could conceivably some kind of Facebook generated ID number. You could do that. There's a lot of organizations out there that when you join them, they assign you an ID number, and that's what you use as your login entry. Okay. But all of these are potential ones, that might work. These ones, probably not, right? Because again, yeah, same name, and again, same date of birth. I mean, I've had classes of like 150 or 200 people where I've had two students with the same name. And I mean, and there's several just Doug Lundquists out in the world, as unlikely as that may sound. It's an odd name, but there's a few of us because the United States is a big country. Okay. So, in general, criteria for identifiers, two things. Number one, something that won't change in value. Okay. So here's what they say: avoid intelligent identifiers, right? Basically, avoid things that'll change. So if your identifier contains a location, right, you say, oh, I'm Doug Lundquist from Chicago. Well, what happens when I move from Chicago to Evanston? Maybe when I live in Chicago, there's only one of me. When I move to Evanston, there's a couple of me. It causes a problem, right? Name too, name could change. Maybe it's unique when you enter it into the system, but perhaps you get married, your name changes to one that's already there, or you get divorced and your name changes, or you just don't like your name and you change it, right? That's a potential problem. And of course, you don't want an identifier that will be null, right? Because if one person's unique identifier can go to null, can go to empty, not existing, then multiple people's can. And then again, those null entries, there's no way to distinguish them. And in general, new simple keys are best, right? So having one field that does it, right? And some of the examples we got here, these are all pretty good. Phone number, that's simple. Email address, simple. SSN, that's simple. ID number, that's simple, right? Better than some long combination of email address, phone number, your name, things like that seem to be unnecessarily complex. Do security questions count? Not really. They tend to repeat, right? So, for example, I mean, potentially, I'm not going to say, so I would say potentially you can come up with a case where they work, but a lot of security questions just have a finite number of answers, right? So finite answers sets are out for that, right? So it's not going to uniquely identify me when they find out that my favorite course in college was Java programming. There's probably a few other people like that. It's not going to uniquely identify me when I say that when I was in 5th grade, I lived on Main Street. Those aren't things. Yeah. Okay. All right. So simple key attributes. All right. So generally when you do the key, it's underlined. So there it is, student ID, that's the identifier, and uniquely identifies the student, right? Student also has a name, student also has whatever other attributes, that's fine. But when it's listed here in the entity box, right, student ID is underlined because that's the unique identifier. And you can have a composite key, right? So here's one. So flight numbers, it's the nature of flights. I don't know if you guys know this, but they repeat flight numbers, right? So one day it could be, Delta flight 26, and maybe a few days later, there's another Delta flight 26. And so if you want to uniquely identify a flight using that available data, the first thing to do would be to get the flight number, but the second thing would be to get the date and somehow combine that into some kind of flight ID, right? Probably just by simple concatenation. So Delta 26, Delta 026 on such and such date. And then you might also include other information like the number of passengers. So in this case, we say flight ID, right? You can see these things are bold. Flight ID is underlined, and right below that, they have in parentheses flight number and date, showing that the identifier is composed of those two fields below. Okay. Last, I think this is, do we have one more slide? Yeah, okay. One more after this. Okay. So in general, when you have attributes, again, singular noun or a noun phrase, something that's simple, easy to understand, as far as possible, something that's unique, right? Although if you have obviously it needs to be unique within its own entity, but sometimes you're going to have data that, you use the same field names, attribute names across different tables, like name is an obvious one, or ID number, that's probably not going to be unique. And within a table, of course, you're going to follow a standard format. So for every flight, the flight number is going to have a standard format, the date's going to have a standard format. You don't want to have some dates be in the, simple 2-digit month, 2-digit day, 4-digit year, and others be in a 2-digit year, because that's going to screw things up when you try to run a query. Okay. And similar attributes of different entity types should use same qualifiers and classes. Okay. So if you have different entity types, right, then if they are similar, one of the easy things to avoid misunderstandings is to use the same kind of attributes, basically, in those tables. So if you have a date field in one table, it's just going to save problems later on by using the same format in other tables. So that, your programmers, they don't get used to writing dates in one table and then do something completely different in another. Or say, if you are going to use a different format, you should have a really good reason for it. All right. And let's see, should we cover? Okay, this is what we're going to cover the next day. So last thing, defining attributes. If you are going to include attributes in your database, right? So first you get the entities, figure out what you need to model, and then within your system, you can figure out which attributes you're actually going to record. So as a sort of a out loud thought exercise, number one, first thing to do, be able to define what the attribute is and why it's important. Why is this thing worth remembering? Number two, what information is being included in the attributes value. So they say, make here clear what is not included, but just, what does the attribute mean? And if you have an idea of what the attribute is, then it should be straightforward, what's going to be included there. Aliases, right? Other names you might use for it, whatever. Where you're going to get the values from, where they're going to derive from. Are the attributes changeable, right? So for example, with a flight name, a flight number, once that flight is launched, it's going to keep that name forever, should not change, right? Same thing for the date. But for this one, student ID, yeah, that probably shouldn't change either. But we'll go back to Facebook. you might decide, hey, Facebook, I'm going to change my email address. And Facebook ought to probably allow for that, because otherwise, if somebody wants to change their email or they lose access to that account, you're going to lose them as a Facebook user. So you want to be able to fix that. Okay. Again, required or optional. We've talked about that somewhat. Related to that, not just required or optional, but also formatting issues, minimum value, maximum value, other types of formatting concerns. And finally, relationships with other attributes. Basically, is this attribute a key field in another table? Right. So again, for Facebook, if the email were part of it's chances are email would not be a key field in another table if you're already using it as a key field for a particular user. But if you're including a zip code field in someone's address, right? Facebook maybe records your physical address and you include a zip code field there. Well, yeah, chances are that zip code is going to link to another table where zip code is the key, is the unique identifier, and then that zip code has a municipality attached to it. So okay, so this is all kind of big picture stuff. I guess we're at the end of our time, which is perfect. So we'll come back and we'll talk more about these modeling issues. Basically, this stuff is that we got on Thursday will be a whole bunch of practice problems, which I hope will be helpful. Okay, well, it's been fun. Thank you for your attendance and attention and participation. If you have any questions, I have a moment, but otherwise, I will see you all Thursday.
Hi, I had a question.
Okay, what you got?